Welcome back to the deep dive. I want you to imagine something for a second. Unless you're driving, of course, please don't do this. But picture yourself in the engine room of a massive ship.
Okay.
Only it's not made of steel, it's digital. There's this screen that just stretches everywhere, and it's filled with glowing charts, cascading graphs, millions of tiny data points just buzzing around like angry bees.
It's a chaotic image, isn't it?
It is.
But that's pretty much what's happening inside your computer at any given moment.
Exactly. And trying to make sense of that storm, that's the topic of our deep dive today, advanced data handling.
Right.
We're talking about the logistics of information. And I know data handling, it sounds a bit dry, but this is basically the difference between a computer that works and one that, just melts.
It really is.
Yeah.
We tend to think of computers as these magic boxes. You ask a question and an answer pops out.
Yeah.
But what we're looking at today is all the heavy lifting that happens in between. How we organize, how we store, and how we get that information back so the digital world doesn't just collapse under its own weight.
And there are, what, 3 big pillars holding that roof up?
Right. The first is performance, which is really just a fancy word for speed.
Right.
If you're building a huge system, like a search engine, you can't have the user wait 5 minutes for a page to load. Computation has to feel instant.
Which leads to the second one, which I think people ignore until something goes wrong. Data integrity.
Oh, it's huge. This is all about accuracy. It's making sure we aren't storing the same file twice. That's redundancy. And more importantly, that the data we pull out is actually the data we put in.
And number 3 is scalability.
Yes. Can your system grow? It's one thing to write a program that handles a 10-item grocery list.
Sure.
But what happens when that list becomes 10 million items? If your system breaks, you fail the scalability test.
So, to figure out how we pass that test, we need the toolkit. We're going to break down the containers we use for data, specifically arrays.
Mm-hmm.
Then we'll get into the why of sorting it all, the quest for the median, and then the main event. We're pitting 3 algorithms against each other: bubble sort, selection sort, and insertion sort.
A bit of a battle royale for efficiency, yeah.
Okay, let's start with the container. The array. When I think of a list, I just picture a notepad, line by line. Is that basically what an array is?
On the surface, yes. A single-dimensional array, a 1D array, is just a linear structure. Think of it like a row of lockers in a school hallway.
Okay, I like that.
Each locker has a number, an index, and inside each one you can store one piece of data, a student's name, a temperature, whatever.
But why lockers? Why not just throw everything in a big bag?
The speed. This is the advanced part. In computer memory, an array is contiguous. That means the computer reserves a block of memory where all the addresses are right next to each other.
Oh, I see.
So it knows if locker 1 is at address 100, then locker 2 is exactly one step away at 101. It doesn't have to go looking for it.
It's virtually next door.
Exactly. Whether you're writing int in Java or int array in C++A, you're telling the machine, hey, give me a solid, unbroken block of memory.
Got it. So that's a straight line. But data isn't always a straight line. Sometimes it's a map or a grid.
Right, and that's where we get to multidimensional arrays.
The grid.
The grid. I always picture a spreadsheet or a chessboard.
That's the perfect visualization. You're going from a single line to a matrix with rows and columns.
Mm-hmm.
So what's the killer use case for this? Why bother with the extra dimension?
Well, think about an image on your screen. What is it, really?
A bunch of pixels.
The grid of pixels. You have a pixel at, say, row 10, column 50. To store that image, you need a 2D array. Or another one in school grades. A 1D list is fine for just student names.
Okay.
But if you want to track student name and their math score and their science score, you need a table. You need that second dimension.
This is where I always get a little tripped up, though. To read a list, I just go down the list. Easy. How does a computer read a grid?
It uses nested loops.
Loops inside of loops?
Yeah. Think of it like a typewriter. You're typing on a line, right? That's your inner loop.
Yeah.
You go character by character across the row.
Uh-huh.
When you get to the end of the row, what do?
Hit enter and go down the next line.
Exactly. That hitting enter is your outer loop. It moves you down to the next row. Then the inner loop starts all over again, going across. So you have a variable, usually called I, for the row, and one called J for the column.
So when I see code that says element 00 is 10 and then element 01 is 20, that's the computer just moving across the first row.
You got it. It's a coordinate system. You need both keys, I and J, to unlock the value.
Okay, so we've got our lockers and our grids. We can store data, but storing it is kind of useless if it's a mess. A phone book with names in a random order is just a doorstop.
I would definitely throw it at you. It'd be useless.
So this gets us to sorting. But before we get to how we sort, I want to talk about why. Besides, finding a name in a phone book, what's the big mathematical reason we need order?
Analysis.
Yeah.
And specifically, what I like to call the quest for the median.
The median. Not the average, the median.
Right, and that's a crucial distinction. The average can be really misleading. If you have 4 people earning minimum wage and 1 billionaire in a room, the average income makes everyone look rich.
Right.
But the median, the value of the person in the exact middle, that tells you the truth about the group.
Okay, so to find that middle person.
You have to line them up first. You absolutely cannot find the median of a jumbled data set. It's mathematically impossible. You have to sort it, either ascending or descending.
That makes sense. If the number for 5, 1, 100, 2, the middle number in that list is 100, but that's definitely not the median.
Exactly. You have to order them. 1, 2, 5, 100. And now the median is, well, this is the tricky part. That list has 4 items, an even number. Where's the middle?
There isn't one. It's a gap between 2 and 5.
Right. So the rule is if the data set length is even, you take the 2 middle values and you average them. If the length is odd, you just pick the one right in the center.
Which means the computer needs a quick way to know if a list is even or odd. And I saw this little bit of math magic in the notes, the modulus operator.
Yeah.
It's a percentage sign.
Yes. The percent sign. Don't let it fool you. It has nothing to do with percentages.
Okay.
In code, percent just means remainder.
Remainder, like from long division in school.
That's exactly it. If I ask, what is 5 modulus 2? I'm just asking if I divide 5 by 2, what's left over?
2 goes into 5 twice, with 1 left over, so 1.
Correct. And here's the trick. Any even number divided by 2 has a remainder of 0. Any odd number has a remainder of 1.
Yeah.
So the code just asks, list length percent 2 equals 0. If that's true, it's even. If not, it's odd. It's a simple, elegant little switch.
I love that. Okay, so we know we need to sort things. Now we get to the main event, the mechanics of movement.
The sorting algorithms themselves.
But before we unleash them, we have to talk about the single most basic move they all make, the swap.
It sounds so simple, right? Swap A and B. But a computer can't just smash 2 values together.
I was displaying this with the bucket analogy. You've got a bucket of red paint and a bucket of blue paint, and you want to switch them.
You can't just pour the blue paint into the red bucket.
No, you get a purple mess. You've just destroyed the red paint.
And that is exactly what happens in memory. If you write a value into a memory slot, the old value is gone. It's overwritten. There is no undo button at that level.
So you need a third bucket, an empty one.
The temp variable. Pour red into the empty temp bucket, pour blue into the now empty red bucket, then pour from the temp bucket into the blue bucket. Done.
It seems like a lot of work just to switch 2 things.
It is. And that's why sorting is expensive for a computer. It can involve millions of these little 3-step dances.
Which brings us to our first contender, bubble sort.
The classic. The one everyone learns first.
So why is it called bubble sort?
It's very visual. Imagine you're sorting numbers from small to large. The algorithm just steps through the list, comparing neighbors 2 at a time.
Okay.
If the one on the left is bigger than the one on the right, it swaps them.
So the big numbers slowly drift to the right.
Exactly. In each pass, the largest number bubbles up to the end of the list, like an air bubble in water.
Let's walk through it. Say we have the list 5, 1, 4, 2, 8.
Okay. First pair, 5 and 1. 5 is bigger. Swap. Now we have 1, 5, 4, 2, 8.
Next pair.
5 and 4. 5 is bigger. Swap. Then 5 and 2. Swap. Finally, 5 and 8. 8 is bigger, so no swap.
And after that first full pass, the 8 is sitting at the very end. It's locked in.
Correct. Then the algorithm just goes back to the start and does it all over again to bubble up the next biggest number.
But wait a minute. If I have a list with 1,000,000 items, does it have to go through the whole thing 1,000,000 times?
Effectively, yes.
Yeah.
This is why we talk about time complexity. Bubble sort is what's called O(n) more, or O(n) squared.
O(n) squared. Break that down for me in, plain English.
It means the work grows exponentially. If you double the amount of data, you don't just double the work, you quadruple it.
Wow.
A list of 10 items takes maybe 100 steps. A list of 1,000 items takes 1,000,000 steps.
So for any large database, bubble sort it's the heat death of the universe.
It would completely freeze the system. It is terribly inefficient for large data sets.
Then why do we even learn it? Why is it in the curriculum?
Because it really teaches you the intuition. It forces you to understand the fundamental cost of that swap operation. Plus, there's a small optimization you can add, a little flag.
The swaps through false thing.
Yeah. It's basically a kill switch. If the algorithm does a full pass through the list and doesn't make a single swap, it realizes, oh, hey, this thing's already sorted, and it just stops early.
Okay, so bubble sort is the brute force method. Let's get more tactical. Selection sort. How is this one different?
Bubble sort is frantic, constant swapping. Selection sort is like a sniper. It's very calculated.
It's a sniper. I like it.
It mentally divides the list into two parts, a sorted section on the left and an unsorted mess on the right.
Mm-hmm.
It then scans the entire unsorted mess, ignoring everything else, just to find the absolute smallest number.
It's hunting for the minimum value.
Exactly. Let's say we have 64, 25, 12, 22, 11. Selection sort scans the whole thing, sees 64, then 25, then 12. Finds 11. It grabs that 11 and swaps it once to the very front.
So instead of a dozen little swaps to move the 11, it just does it in one clean shot.
Precisely. It minimizes the number of writes to memory. If writing to memory is an expensive operation for your system, selection sort is cheaper than bubble sort.
But it still has to scan the whole unsorted list every single time, right?
Unfortunately, yes. It still has that ON complexity when it comes to comparisons. It's always looking at everything, even if it isn't moving everything.
Okay, so bubble swaps too much, selection scans too much. Let's bring in our third challenger, insertion sort.
Insertion sort is probably my favorite of the simple sorts, because it's how we as humans actually think. Imagine you're holding a hand of playing cards.
Okay.
You pick up one card, then you pick up a second. You don't scan the whole deck. You just look at the card in your hand and ask, does this go before or after the one I'm already holding? You just slide it into place.
The key word there is slide or shift.
Yes. Insertion sort starts at the beginning. It takes the next unsorted number, the key, and it looks backwards into the sorted pile. If the key is smaller, it just shifts the larger numbers to the right to make a hole for it.
So it's not really swapping A and B. It's more like scooting B, C, and D over to make room for A.
Exactly. And this is why insertion sort is special. It's adaptive.
Adapted.
It adapts to the data it's given. If your list is already partially sorted, insertion sort barely has to do any work. It picks up a number, sees it's already in the right spot compared to the previous one, and just moves on.
So unlike selection sort, which blindly scans everything no matter what, insertion sort is.
Oh.
It's smart enough to be lazy.
And being lazy is a virtue in computing. It makes it incredibly fast for small data sets or for data sets that are almost sorted already. It also uses almost no extra memory.
So if I have a massive log file that's mostly in order, but a few entries got mixed up, insertion sort is the hero.
Absolutely. Bubble sort would just churn away. Selection sort would scan blindly, but insertion sort would just zip through and fix the few mistakes.
Okay, so we've covered the containers, we've covered the algorithms, but we have to talk about the danger zone. We mentioned data integrity earlier, but there's a scenario in our notes called parallel arrays. And this sounds like a disaster waiting to happen.
It is the trap. It's the one that catches almost every new programmer at least once.
So set the scene. What are parallel arrays?
Imagine you have two separate lists. One is names and one is ages. So names at index 0 is Alice, and ages at index 0 is 25.
Got it.
Names at 1 is Bob, ages at 1 is 30. The only thing linking Alice to her age is that they both have the same index number, 0.
So position 0 means Alice and position 0 means 25, but they're in totally separate buckets.
Exactly. Now let's say you want to sort this whole data set by age. You run your sorting algorithm, let's say insertion sort on, just the ages array. Okay, so 25, 30, 20, it sorts that to 20, 25, 30.
Great, the ages are sorted. But what happened to the names?
Well, if I didn't sort the names array, names at index 0 is still Alice.
Exactly. So now, name 0 is Alice, but ages 0 is 20. Alice just got 5 years younger, and Charlie at the end is now somehow 30.
We just completely corrupted the database.
Completely. You have broken the relationship between the data points. In a classroom, that's annoying. Alice gets the wrong grade.
But let's scale this up.
Yeah, let's go back to that hospital example.
You have an array of patient tides. You have a parallel array of blood types. A nurse clicks sort by ID to find someone. The algorithm sorts the IDs perfectly, but it fails to perform the same swaps on the blood types array.
So patient A is now listed as being O positive, but they're actually B negative.
And you authorize a transfusion.
That is genuinely terrifying. It's not just a computer bug, it's malpractice.
And this is why parallel arrays are considered so risky, and why modern programming uses structures like objects or classes containers that bind the name and the age together so they can never be separated. But understanding why we moved away from them is so important. You have to see the fragility of the data to appreciate the better structures we use today.
It's the lesson of the key. If you move the key, you have to move the value with it.
Precisely. If you swap a Jesse with ages J, you must, in the very next step, swap Nemesi with names J. They have to move in lockstep.
It really just highlights that advanced data handling isn't just about shuffling numbers around, it's about preserving truth.
That's the real so what of this whole deep dive. Whether it's the temp bucket protecting data during a swap, or choosing insertion sort to save energy, or handling parallel arrays to, save lives,
Yeah.
it all comes down to integrity.
We started this by picturing an engine room. I feel like we've pretty much taken the engine apart and put it back together.
And hopefully we didn't have any leftover screws.
Hopefully not. But it leaves me with a final thought for everyone listening. We live in a world of sort by price, sort by rating, sort by date. We click those buttons a dozen times a day without even thinking about it.
We take it completely for granted.
But behind that one click is this frantic, high-speed ballet. Variable swapping, memory being overwritten, comparisons bubbling up and shifting down. And if just one tiny piece of logic fails in that parallel array sync,
The reality you see on your screen stops matching the reality in the actual world.
so the next time you sort your playlist or your bank transactions, maybe just spare a thought for the algorithms working in the dark just to make sure Alice stays 25. Thanks for listening to The Deep Dive.
We'll see you next time.